In 2009, he won the Huddle Report. It is a NFL draft competition graded by draft experts. And he did this in his dorm room, and he won this competition. Then later, he worked for a professional sports team working on their draft, where the draft he worked on was declared by many illustrations as the best draft in the league of the entire NFL. So he did this for fantasy, and then did it in real life. Everyone, please welcome Mike.
Today, I'm here to talk to you about the work we do at NFL Next Gen Stats. My name is Mike Band. I'm the Senior Research and Analytics Manager for NFL Next Gen Stats. And today, I'm going to talk about the many models in production at Next Gen Stats. So this will be the fourth time I've spoken at the New York R Conference. And each time I've sort of updated the story of the Next Gen Stats world. When I first talked at the New York R Conference in 2019, we had one model in production, and that's the model that I talked about, completion probability. Today, we're going to go through the many models that are now in production, 15 in total, and we're going to take a quick journey through what is next-gen stats, the evolution of our toolbox, and then the many models in production. So let's start with the question, what is next-gen stats? Next-gen stats is the real-time player tracking data collection team. We are the NFL, and so the NFL owns the property, and we distribute our data for a variety of reasons. So it's for broadcast use, for the teams themselves, and for the league office to make the game better. So what you could imagine is we have RFID sensors in every player's shoulder pads, tracking their X, Y, speed, direction, all of these data points every 10th of a second for every play on the field. This equates to millions of data points per game that we have to munge and find data for. So with all of this data, we are able to create a significant number of metrics. And as you can see on the left, that is a play that we can recreate on a two-dimensional dots with our data. So the play on the left is the longest pass completed in the next-gen stats era since 2016. And I'll go deeper into this play on how we can break down some of the stats within it. So who's using next-gen stats data? Well, first we got to start with the broadcast and how do we engage fans with better data and more valid metrics. So this is going beyond the box score of yards and touchdowns and tackles to more complex metrics like the ones we're going to talk about today. All 32 teams are using this data, whether it's picking players in the draft or free agency, whether it's finding the weaknesses in your defense, whether it's finding tendencies in your own team. They're trying to use this player tracking data to make their team better, to make better decisions when it comes to their roster, and overall make their processes in season and out of season more efficient. And finally, the league office. So we have an office in New York and we have an office in LA. The LA office is more of the NFL media group where Next-Gen Stats is located. At the New York league office, that group is doing way more work to try to make the game better through rules or player safety initiatives. Tom Bliss and Allie Blake are both in the studio audience today, and it's been great to see the league office really leverage the player tracking technology to make the game better. So before we dive into all the models, I would love to take you through a history of the evolution of the stats toolbox at Next-Gen Stats. So we started with a question: what stats can we create if we have player tracking data every 10th of a second for every play? Well, our inaugural season, which was the 2015 season when we finally had sensors in every stadium, we were able to create basic stats like top speed, distance traveled, or participation, like how many snaps did a player play. Before that, that was done by manual human data labeling in the stadium every game. Now, we can use technology to say who's on the field. But then we sort of had to get more advanced with our toolbox. We tried to look into what can we create if we take the raw tracking data, merge it with our traditional football stats, we call it GSIS, and can we then extract more meaningful logic-based stats? This would be air yards, which would be the distance a pass travels downfield, or separation, which would measure the receiver's distance to the nearest cornerback. All of these stats help us get a lot of more advanced stats without having to need machine learning modeling. But then, over the years, and especially with the help of the open source competition, the Big Data Bowl, we have dived into a much more advanced set of statistics that cover a variety of different aspects of the game of football. So what we started with was speed and distance. Now we have measures like completion probability, expected yards, coverage classification, win probability. We can even say whether or not a team should go for it on 4th down. And today, we have now 15 models, active models in production that we have to maintain. Now we have different questions to ask. How often do we retrain our models? Is our architecture as efficient as possible? Are the dependencies that our model's built on good enough or up to date? All of these questions mean that we're not only creating new models, we have to maintain our existing ones. And so today, I'm going to go through our list of the many models in production at Next-Gen Stats. So what you're about to see is an intimidating slide. It's got all of the stats currently in production. So we can start with completion probability. What's the odds of a pass being completed? Or expected rushing yards in YAC, which estimates the number of yards that a ball carrier would gain. Let's start with a simpler list. So these 5 stats I'm going to go through a little bit more detail, talk about the model types, the training set, the features that go into it, and all the little decisions that we made. And we'll also give examples of what it looks like in actual broadcast. Now, as I go through each of these models, there's key assumptions and considerations that we have to take account for. The first, these models have to generate predictions in real time or near real time. So after the play is processed, after the play ends, we have to be able to hit the model and create an aggregate or create a result or a prediction. 2, the model must be explainable, or at least the problem matches our intuition. What do I mean? Well, if we can use tabular data to solve a problem, we will, because we can understand the features that go into it. And certainly your football expertise is going to dictate what features you end up engineering out of the player tracking data. But if we do use neural networks and deep learning techniques, does the problem match the problem statement? Does the architecture match the problem? That's the key to, if we were to use deep learning, and I'll go through some of those neural networks that we have in production, how can we best understand what the model's doing? And third, the model must pass the eye test. This is probably the most important part, especially for our researchers and analysts who have to sell this data and say that this stat matters because. And the only way to get football people to really grab onto a stat is if it makes sense when you see it. So when you see a pass that's very difficult to complete and it says the model says 75%, you know something's wrong in the data, even if the scoring evaluation metrics are good. So we do a lot of human labeling or human relabeling to identify what perhaps could be the issue in the model. So let's start with completion probability. The question that this model is trying to answer, what are the chances a given pass will be completed based off of the difficulty of the throw? So the model we used is an XGBoost model. The features that go into it, you can see on the right with the SHAP plot. So we have how far the ball traveled in the air, the separation the receiver had from the nearest defender when the ball arrived, how fast the quarterback and the receiver were going, the location of the quarterback when he threw the football and the receiver when they threw the football, and much more. We had a target variable of a Boolean if the pass was completed, 1, and if the pass was incomplete, 0. And we used the 2018 to 2021 seasons as a training set, and then we would use the 22 regular season as the test and 22 postseason as the validation set. So what can we do with this data in real time? So you can see on the right, this is a play example of one of the longest passes in the NFL over the last 10 years. So the pass, this play happened in a Carolina Panthers-Atlanta Falcons game. At the end of the game, the Panthers needed a touchdown. They were down by 6, it's 20 seconds left, and you can see Philip Walker rolls out to his left and finds DJ Moore downfield for a 62-yard touchdown. Our model said that the completion probability was 11.5%, the fourth lowest completion probability of any completion during the season. And you can see the leading factor, air distance, 67.6 yards in the air, as the crow flies, you could say. From the point the quarterback threw the ball to the moment the ball arrived at the receiver, the ball traveled 67.6 yards in the air. So not only can we use completion probability to contextualize a play, but we can also break down the features that go into it. Now we'll talk about expected yards. Estimate the number of yards a ball carrier would gain from the moment they receive the ball. And within expected yards, we've found that we need separate models for every separate situation. The reason is because the distributions of outcomes are different for these different situations. So whatever you train on, those distributions you can see on the left versus the right in that graph, the distributions are going to give you different results. So if we created a single model for both kick return and punt return plays, we would have a biased model. So what we have for expected yards, we have different models for each group. We have 5 in total. Expected rushing yards on a handoff, expected yards after catch. We also have expected rushing yards on a scramble, so when a quarterback tries to scramble from the pocket, we can measure that prediction. We have expected yards after catch, which represents the receiver once they catch a ball, how many yards will they gain. And then last year, we launched expected return yards, which predicts kick and punt return yardage. As you can see, the architecture we used was a convolutional neural network, and we use a technique called pooling, where you take the XY, the speed, direction, and you create a matrix of every player relative to every other player on the field. And this architecture was actually created by the Big Data Bowl winners in 2019 when they won the expected rushing yards competition. And they were 2 Austrian data scientists who had the thought of how can we simplify this problem? A dot has to get from here to there with a lot of things in the way. It's almost like a video game, you could say. And so they created this technique. They didn't have to engineer a single feature. So when all of the other entries were engineering features like how many players were in the box, how close was the nearest defender when they got the ball, the CNN architecture blew the other entries out of the water in terms of its predictive performance. And what we found was that architecture was very useful in all of these situations. So we keep going back to the CNN and the pooling technique because it matches the intuition of the problem. If you have the locates of every player relative to everyone else, then you can measure an expectation of yards gained. So let's take this example. In this example, you'll see Raiders running back Josh Jacobs get a handoff around the 35-yard line, and the line of scrimmage is at the 30. Now, the question we're asking the model is, how many yards will this running back gain on the play? So let's show the moment that we are running inference. So we have the dots and the locations of every player when they receive the ball. So what we're going to do is we're going to make a prediction. We're going to expect a 3-yard gain, so he gains 3 yards past the 30. So we expect him to get right to about the 27-yard line, if you could see that on that field. He actually gained 30 yards on the play. So you can see on the right how many defenders he has to evade to create this touchdown play. Now, on the stat sheet, it's going to look like a 27-yard touchdown. or a 30-yard touchdown. But when we evaluate how many yards the average runner would gain in that situation, we find that he outperforms expectation by 27 yards. Not only can we find the estimate of the expected yardage number, we can also predict the odds of a first down, the odds of a touchdown. And what this does is it creates significant contextual features, contextual stats that more exemplifies what happened on the field. Our next model I'm going to talk about is receiver route classification. So what route type did a receiver run on a given play? So as you can see, this was another derivative of the Big Data Bowl. Nathan Sturkin, who's now a data scientist with the Cleveland Browns, won the competition and only less than a year later was hired by the Browns. He came up with a combination of a CNN and LSTM model that takes the player locate data of each eligible receiver and predicts one of 15 groups. If you're a wideout, 10 wideout routes, and if you're in the backfield, 5 backfield routes. And what we did is we created a prediction for what route did you run out of those labels. And now we're able to do a lot of splits, you could say, of what route a receiver ran. On the right, you'll see a diagram of all of the route types for a wide receiver, and you can see the archetype of the player paths over that time. So what we did is we take the moment of snap to either the end of the pass or 4.6 seconds, because anything beyond that, they're running around like a backyard play. And we're able to use that time span for each individual player, what route did you run? Now we're going to go into coverage classification, which is a little bit similar to route recognition, but at the team level. So what coverage type did a team run on defense? As you can see on the right, Tom Bliss, who's in the crowd today, spoke last year at the New York R Conference. He created the baseline model that became our coverage classification model. So thank you, Tom. What we used was a CNN attention model, and we took the temporal locates of every player on defense from the snap to our 4.6 seconds. And we also took the relative positioning of all players relative to all other players, as taking that from the pooling technique we learned from expected yards. We were able to classify 8 different types, so whether it was cover 0, cover 1, cover 2, which are man coverage, and then you also have cover 2, cover 3, cover 4, cover 6, which are zone coverage. On the right is a diagram of those man coverage, or the first 4 coverage types. So the top left is going to be cover 0 man. You can see that everybody is responsible for an eligible receiver. Cover 1 man, you're going to see a safety who's patrolling the middle of the field. Now you could imagine that the movements of the players will be representative of the play call. And so that's why we can take the play level player tracking data, take manual labels of saying that they're in cover 1, cover 2, and be able to train a model to find those patterns to identify those coverages. This is what the CNN looks like. So there's a lot of layers that went into it. And we use a self-attention model in this case that proved to be the most compelling predictions. Win probability. What's the odds of a team winning the game at any moment in the game? So this is an XGBoost model. We found that engineering features was important here. So we looked at the score differential, the time remaining, how many timeouts were left. We looked at how the quality of the team. So we have a measure of, if the Chiefs and Patrick Mahomes are playing the Buccaneers without Tom Brady, that line is the team strength is going to be indicative within this model. So our target output is 1 is a win, 0 is a loss. And over time, the game, you can see the win probability fluctuate for every play. On the right, you'll see a image of the Minnesota Vikings' historical comeback last season, where they were down 33 points in the second half and came back to win. Their win probability in that game got to as low as 0.4%. It was the second lowest win probability comeback of any game in the next-gen stats era. So we're able to quantify the significance, the context behind these crazy comebacks. That's a wrap on all of the models that I was here to talk about today. I came here to talk about the many and only had time to talk about few. If you have any questions, please, I'll be around all during these 2 days and happy to answer any more details of any of the models I talked about today. I encourage you to, if you're a Twitter user, to follow the NextGen Stats Twitter account. We are hot and heavy during the football season with a ton of the visualizations that you saw in today's presentation. You can follow me on Twitter, but mostly I like to consider myself the ghostwriter of NextGen Stats, so that should be enough. Or you can follow us on Instagram if you prefer that. Thank you.